Thanks very much. It's a huge honor and pleasure to be here. So I'm going to see how much I can cover today. I have also put in a little one slide at the end, a controversial one on how quantum and AI maybe relate, but we'll see if we get time to cover that. So my talk is about accelerating scientific discovery with AI. DeepMind was founded in 2010, and it's a kind of Apollo program effort to build artificial general intelligence, which we call AGI. And what that means is general purpose AI systems that exhibit all the cognitive capabilities that the average human has. So that will be a huge milestone, I think, in AI research. The mission of DeepMind, and now Google DeepMind, is to build AI responsibly for the benefit of all humanity. And we started actually with games, many of you know. Our first big landmark result was in 2015 and 2016 with our program AlphaGo, which was our learning system that mastered the game of Go through a process of self-learning, and actually inspired a lot of the modern AI work that we see today. So why is Go so important? Well, of course, most of you will know Deep Blue beat Garry Kasparov in chess in the 90s, but it took another 20 years for Go to be cracked. And the reason is Go is a far more complex game than chess. One indication of that is there are 10 to the power 170 possible positions in Go, which of course is a lot more than there are atoms in the universe. So there's no way you could enumerate all possibilities in order to determine what the best move was in a particular game. And in fact, it was thought that Go was so complex, it was at least a decade or more away before a Go program would be able to be a professional, let alone the world champion. And in 2016, we actually had a famous $1 million challenge match in Seoul in South Korea that was watched by over 200 million people around the world. AlphaGo won the match 4-1. And it was not only did it win the match, it also made some creative new moves, creative strategies that had never been seen before, even though we as humans have played Go for over 3,000 years and professionally for several hundred years. So it's one of the most studied domains in human endeavor. And yet AlphaGo was able to come up with new strategies like the famous move 37 in game 2, which won it game 2. Now, I'm just going to quickly outline how AlphaGo worked, because it's going to be important when I talk about what the future of AI is at the cutting edge today. And some of these ideas are coming back into importance now. So the way we trained AlphaGo and successive versions of AlphaGo that we called AlphaZero was we started off by having a random neural network initialized randomly, and we got it to play 100,000 games against itself. And that creates a data set with which to train a version 2 of the system. So what the version 2 is trying to do is predict what moves the version 1 would make in a particular situation, a particular position, what were the more likely moves, and also what was the probability of which side would win the game at the end of the game. So if you can predict those two things, you can start really restricting that enormous search space down to something tractable, okay, in a reasonable amount of time. And so what happens, you train a version 2, and version 2, based on that version 1 data, is slightly better than version 1. And you enumerate how much better by having a little 100-game match-off between version 1 and version 2. And if version 2 beats version 1 by a certain statistical threshold, 55% win rate in this case, then you replace the generator of the next data with version 2. So you replace version 1 with version 2. And then you go around, you generate a new piece of data. Don't forget, you play another 100,000 self-play games now with version 2, so that the quality of the games is slightly better than with version 1. And now you train a version 3 to predict what version 2 did. And actually, it turns out, doing this 17 times, 17 epochs, you go from playing randomly to stronger than any entity in the history of the world has played Go. And you can actually do it in less than 8 hours on modern computers. So you actually can see this evolution in real time, which is quite incredible to watch. Obviously, if at any stage the new version doesn't beat the old version, then you just play another 100,000 games with the old version, and you add that to the database. So now you have 200,000 games to predict to train the new version. So it's a very powerful system, self-learning system. So what this means is you can take this model of Go, and if you imagine each node in this search tree is a position in a Go game, and you're trying to, maybe you're in the current position at the top of this tree, and there's this enormous, almost, intractable a number of possibilities from the current position. But you only have a certain amount of time to search a very small fraction of these branches, say the ones in blue here. And then you eventually, when you run out of time, say 1 minute or of computational time, you now need to output the best continuation, the most likely best move, which is the one in pink. So this is then using this model to efficiently guide this search process. And I'll come back to this system, which is very general, in a moment. So we used games as a proving ground. They're kind of like the perfect proving ground in the early stages of DeepMind to prove out these algorithmic ideas in a very efficient, quick way. So it's very easy to see in games whether you're progressing. They have clear metrics, obviously winning games or adjudicating or gaining points. So it's very easy to see if your algorithms are making progress. But of course, it's just a means to an end. This is not the end in itself. We wanted to generate general algorithms that would transfer to real-world problems, not just be good at games. And we had all these landmark results in all different games, ranging from very simple Atari games all the way to the most complex real-time strategy games that you can get on computers today. And programs like AlphaZero that were able to play not just Go or chess, but any two-player information game, perfect information game, to better than world champion level. So once we'd done these breakthroughs, it was time to, around 2016, 2017, to turn our attention to more serious problems using the techniques we'd learned from games. So this has always been my passion, and why I've worked on AI my whole life, is to use it as a tool to help us accelerate scientific discovery itself. So what do we look for when we're choosing a problem, a suitable problem that is suitable for these types of methods? Well, there's 3 criteria that I generally look for. One is being able to describe the problem and sort of articulate it as this search through a massive combinatorial search space or solution space. That's actually good for these types of methods. You need to have a clear objective function or metric that you can optimize and hill climb against. And then, of course, you need either a lot of data to learn from, to learn the model, or, and ideally, an accurate and efficient simulator, so you can generate more synthetic data from the correct distribution. And it turns out, actually, a lot of problems in science can be couched and thought about in this way. And the first one that was on my list, and I've been sort of thinking about actually for more than 20 years since I first came across the problem, was the famous grand challenge in biology of the protein folding problem. Predicting the 3D structure of a protein just purely from its amino acid sequence. So most of the biologists in the room, of course, will know about this, but for those that are not familiar with this problem, you get a sequence like the one on the left, this amino acid sequence. You can think of it roughly as the genetic sequence of the protein. And then you want to immediately predict this exquisite shape on the right. That's what that protein looks like in the body on the right. And of course, the 3D structure of the protein tells you quite a lot about the function. It's not the only thing that tells you about the function of the protein, but it tells you a lot about it. So if we could crack this, then it would be very useful for things like drug discovery and fundamental understanding of biological mechanisms. So AlphaFold 2, which we produced in 2020, was sort of acclaimed by the experts in the field as a solution to this long-standing problem in computational biology. And we were able to predict the accuracy of these predictions in most proteins down to an average error of less than 1 angstrom. So that was always the threshold, so it would be useful for biologists, is it needed to be competitive with experimental error. So we went on, and then we ended up over the next year, because this system was not only accurate, it is incredibly fast, we actually ended up folding all 200 million proteins currently known to science. And we continue to fold all the new ones that are genetic sequences that are discovered every year, and add them to an open source database that's free for everyone to use, that some of my colleagues in the room maintain at EMBL EBI in Europe. And over 2 million biology researchers and medics have made use of the predictions, and it's had over 25,000 citations so far. So it's really had an enormous impact on the structural biology field. And I really, we've also collaborated ourselves on certain projects. There's a few that listed up on the screen, but I'm really especially proud of our work with neglected diseases, specifically the DNDi, which is part of the WHO, where we look at neglected diseases in the poorer parts of the world, Global South and others, where we can accelerate some drug discovery by giving them the structured proteins in the viruses or the bacteria and actually allow them to go straight to drug discovery, where Big Pharma has not invested in those areas or those diseases. So it's been really rewarding actually seeing the incredible range of things scientists have used the predictions and also the underlying model for. We continue to make progress with these systems. We just released AlphaFold 3 earlier this year. And what we're trying to do now, of course, is that biology is obviously not a static system. So you can think of AlphaFold 2 as giving you back the static snapshot of what these structures of proteins look like. But biology is a dynamic system. It's really what's important is how these structures and these molecules interact with each other. And AlphaFold 3 is our next step towards that by looking at making predictions between pairwise interactions between proteins and proteins, but also proteins and small molecules, including like drug molecules, and also proteins and RNA, proteins and DNA. So we can start thinking about this is the beginning of building up maybe a virtual cell simulation of a virtual cell or something that could predict a virtual cell perhaps in 10 years' time. We've also done a lot of work much more broadly than AI with biology. Here's just a selection of some of the work we've done in the sciences and mathematics, but also medical things like diagnosing retinal disease from retinal scans. And also we've done a lot of work that's helpful for climate, including work in collaboration with EPFL on containing plasma and fusion reactors, and also weather forecasting. So we have a state-of-the-art weather forecasting system called GraphCast that forecasts 10-day weather predictions much more accurately than traditional Navier-Stokes methods and far more quickly. We're also doing things like designing new materials with new properties and trying to predict those properties ahead of time. So that's just what we're doing on AI for science. There's also a whole nother branch, which is the path to AGI and also tools for creativity and productivity. We've been working on all those types of tools too. Of course, you'll all be familiar with generative AI models. We have our own state-of-the-art models in image generation and video generation and also music generation. It's kind of, we've all got used to them now, but it's still kind of mind-blowing, I think, if you think 5-10 years back, that you would have AI systems that can sort of generate, realistic pictures and videos and creative things like music just from text prompts. Of course, a lot of the attention right now is on what we call multimodal foundational models. Foundation models, they're more general than large language models, which I'm sure you've all used and interacted with, the chatbots. And this is the next generation of which our program, Gemini, is one of the most capable, and it allows you to reason over not just text, but also multimodally over images, audio, video, and code. So it's bringing together all of these different modalities that we as human beings interact in. And for a system to be truly useful, I think it has to understand the full context that we're in. And so what we started as a prototype, and a very exciting prototype this year, is what we call Project Astra, which is this idea of a universal AI assistant that is helpful in everyday life and can help do things like recommend things or do admin chores that you don't want to do, and maybe even in the sciences be a kind of research assistant. I've just got a quick video here, 2-minute video of how that looks. It's a very early prototype of the types of capabilities this sort of system, Project Astra, which is built on Gemini, is able to do in the real world as a demo.
Okay, let's do some tests. Tell me when you see something that makes sound.
I see a speaker, which makes sound.
What is that part of the speaker called?
That is the tweeter. It produces high-frequency sounds.
Give me a creative alliteration about these.
Creative crayons color cheerfully. They certainly craft colorful creations.
What does that part of the code do?
This code defines encryption and decryption functions. It seems to use AES-CBC encryption to encode and decode data based on a key and an initialization vector, IV.
That's right. What neighborhood do you think I'm in?
This appears to be the King's Cross area of London. It is known for its railway station and transportation connections.
Do you remember where you saw my glasses?
Yes, I do. Your glasses were on the desk near a red apple.
What can I add here to make this system faster?
Adding a cache between the server and database could improve speed.
What does this remind you of?
Schrodinger's cat.
All right, give me a band name for this duo.
Golden Stripes.
Nice. Thanks, Gemini.
You can see that's just the beginning of what an assistant that fully understands your context could help with. And so that's the start, and it's sort of quite fun right now, but you could imagine this being something that maybe you would use during your everyday life on glass or some kind of form factor, and it'll kind of carry around with you. So what's happening in the future now then is actually I think the next big breakthroughs, and you're going to see in the next year or two, and we're working very hard on, is what we call agent-based systems. So these are systems that don't just do Q&A and sort of passively respond to your question, but actually can actively do things in the world for you. So these are systems that can plan and reason, and they can act in the world and maybe carry out tasks or solve objectives for you. And so what we really need is basically a combination of the AlphaGo system I showed you at the start and the current Gemini models. And that's what we're working on, is combining the strengths of these planning systems with these world models like Gemini. So instead of planning over a game model, you're planning over language and this multimodal model. So just to step back and just the last couple of minutes, and to maybe just be a little bit provocative, and obviously with huge respect to my quantum colleagues who with fascinating talks in the last session, I've been thinking for a long time, actually since AlphaGo, what are we actually doing here, and what are the limits of classical systems? So, I think it's fair to say that classical Turing machines can do much more than we previously thought. So what's made me sort of think about this, and I see ourselves as a bit like a Turing's champion, pushing the limits of what classical systems, embodied by Turing machines can do. And I think one of the things actually Professor Block mentioned remind me of the way a lot of quantum computing folks see classical computing, with this sort of seemingly plausible, but I think in my opinion, a little bit outdated view that if to simulate a quantum system, one would have to naively sort of do it in a naive brute force way. And actually, I think you can instead do it in a much more elegant way where you model the underlying structure that is there. And unless, of course, you could be in situations where there's no underlying structure, and then you've got no alternative but to enumerate all the states. And if all the states are truly independent or random, then there's no structure to learn. But my conjecture would be that, most natural systems, or maybe all, but I would say almost all, and patterns that occur in nature have some underlying structure. And that's potentially, I think, efficiently discoverable and modelable by a classic algorithm, classic computing algorithm, learning algorithm. So, if that's true, I think that has big implications potentially for complexity theory, including P equals MP, and maybe even some fundamental physics and things like the definition of information and entropy. But, maybe it'd be an interesting thing to talk about in the next coffee break. But I think one thing that complexity theorists have sort of overlooked is the idea of doing a massive amount of pre-compute up front before asking it at test time for a solution. And that's effectively what's going on here with these neural network models, is we're doing this huge amount of pre-compute up front, training the model, and then we're using the model in this very efficient way at test time to answer a novel question. And I think that this allows us to sort of get around some of the problems that people have classically thought about with traditional computing systems. So then I'll just end then with just the responsibility question, which we touched on a lot yesterday in the discussions. I think AI has this incredible potential to help with humanity's greatest challenges, from medicine to climate. but of course it has to be built responsibly and safely and be used for the benefit of everyone. And as I mentioned yesterday, for those of you at the talk yesterday, I think we should not move fast and break things with AI. I think it's too important, too profound a technology, and instead we should really lean heavily on the scientific method. And I think a transformative technology like AGI requires exceptional care, almost sort of reverence about what it can do. But we also need to be bold with what can be done with it, so that we can get all of the benefits that we desperately need as a society to tackle some of our biggest challenges. So we need to be bold and responsible, I would say. And then finally, in the limit, my dream has always been, if we build AGI, then it could be, you can sort of think of it as the ultimate general purpose tool to help us understand the universe. Thank you.